Now take a look at another really important property of the gradient. And again, this one has some pretty significant geometric interpretations. And so let's start. I am going to sketch a surface, and just to make it easy, I'm going to make it look like some kind of bowl. So let's say this is our surface. Right, and let's say this surface now, I mean, it probably the most general way to describe a surface is if it's described implicitly, so we don't have to isolate for any variables. So let's say that the equation for this surface is like f of x comma y comma z is equal to some constant, right? So c is some constant. So basically all our variables are here. We can still assume that z is dependent on x and y, but we just have all our variables collected on one side, and so we have our implicit definition of the surface. Now, on this surface, again, think about like this bowl. I could draw, and we've talked about these level curves. I could draw a level curve anywhere on this bowl. So, it'd probably just go all the way around. Let's say something like that, right? So this is going to be a level curve. So I'm going to call this r of t, because remember, we now have a way of representing curves in vector form. So I'm going to say that this is our function, and it's going to be some x. So we're going to have some function for x component, some function for y, some function for our z, right? So this will be any level curve, right? So any level curve, let's just say at level k, right? Where again, k is some constant. And we're going to assume that obviously once we're drawing it on the surface, then everything is well defined. So what that means is, so because the curve is always on the surface, it means that the parametric equations for the curve must satisfy the equation for the surface, right? And we kind of did this previously, like when you have a curve and you wanted to figure out like where it intersected a plane, right? And you were trying to find, let's say, a point or two. But now what's happening is, since our curve is always on the surface, then the parametric equations for the curve must always satisfy the equation for the surface. So we can write this. So since r of t lies entirely, it's always, oh come on, lies entirely on the surface, then for all t, if I plug in my parametric equations for x, y, and z into the equation of the surface, then I will get an identity. In other words, I will always get c. So what's implied is this: f of x of t comma y of t comma z of t, that must be equal to c. All right. Okay, so what good is this? Well, what we are going to do, and again, you could say we're just doing this, for exploratory reasons, or just because we want to, or because derivatives are fun. Let's differentiate both sides of this equation and see what happens, right? Again, we are mathematical explorers. We're going to, venture into uncharted territory and see what happens. So let's see if we can differentiate both sides with respect to t. Now, clearly, just having a constant over here, this side is super easy to differentiate. This side, a little bit more involved. So let's kind of think of how we could possibly come up with an expression for the derivative of this side with respect to t. Well, look at this. Our surface is a function of x, y, and z. And then the components of our curve are functions of t. That smells like the chain rule again. It almost seems like I could say, here's my surface, big F. Big F depends on x, y, and z. So there are my three variables, right? In other words, these three variables define all the points that make up my surface. They have an x, they have a y, they have a z. But then on any level curve, and again, it could be any of them. I just drew one, but on any level curve, we can express that curve parametrically. So then x will be a function of t, y will be a function of t, and z will be a function of t. So the chain rule gives me a way of writing down what the derivative of this function is, or f function, which is our surface, with respect to t. And again, it depends on all these different partial derivatives that we can label our tree. So let's go ahead and again decorate our tree. So along this branch, it'll be d big F dx. The middle branch here, from f to y, will have a rate of change of d big F dy. And then this one over here will have df big F dz, right? And then along each of these lower branches, this one will have just a dx dt. This one will have a dy dt. And then this one will have a dz dt. And the chain rule says if I want the derivative of f with respect to t, I have to multiply some things and add them together. So I need to multiply these two, and then these two. So multiply along the branches of the same color, and then add the multicolors together to get one nice expression. So if we now differentiate this equation, both sides, right? So if we differentiate with respect to t, this is what we will get. So I'm gonna write down the complicated stuff on the left, and then of course we know we're gonna get a 0 on the right. So I have df dx times dx dt, and then plus df dy times dy dt, and then finally plus df dz times dz. I was like mid-partial, mid-regular d there, but let's just do the regular d, dz dt. So that's what the left-hand side looks like when I differentiate it. Why? Because of the chain rule, right? Right? The chain rule, what it does, it gives us this procedure of writing down the derivative, right, of complicated functions and surfaces, again, in a fairly efficient way, but then our equals, and then the derivative of our constant here is 0. All right? Okay, so what have we done? Well, like I said, we've now written down this important equation, and what it shows is it shows an expression on the left-hand side that I can actually interpret as a dot product. Because again, it looks like I can see where we're multiplying three pairs of things and then adding them all together. It sounds like if I were to have a vector where I have my partials here, so there, and there, and there, right? So that would be one vector. And then if I made another vector with components dx dt and dy dt and dz dt, right? And if I said take the dot product of these two vectors, then I would get the expression right here. I would get the same expression that our chain rule gives us, and it would still have to be 0, right? But let's think about what these two vectors represent. This one is clearly a gradient, right? It's a gradient, and in fact, it's the gradient of that surface. Because what I'm doing is I'm taking my f function and I am differentiating it with respect to x, differentiating it with respect to y, differentiating it with respect to z, and I'm forming this vector. So this is actually, let's write this down. So this is actually the gradient of our surface. So the gradient of f. Let's think about what this means now. So this is where we have to think about our curve. The curve had original components x, y, z. Well, we know, and then over here we see this vector that has components dx dt, dy dz, dz dt. Well, that's just the first derivative of r. So this vector here is r prime. And there are several ways you can interpret it. You can talk about velocity, but just more generally, this vector here is the tangent vector, right? This is our tangent vector to r of t. So we can actually, so I'm going to start by sketching the tangent vector. So I'm going to go back up here, and basically I'm going to sketch the tangent vectors in blue, so you might have one here. Now, these are not your unit tangent. In fact, let me make this one a little bit, let's go back up here. So these are not your unit tangent, so they're not necessarily of constant length. So some might be longer, some might be shorter, and like this. Like that, right? So those are your tangent vectors, right? Now, remember, what we're trying to get at is another property of the gradient. So we're going to have to kind of interpret what this equation is saying. But it shouldn't be too hard to interpret it, because what we're saying is that the gradient of the surface and the tangent vector, right, to each of the level curves, and this could be at any level, right? We're not saying any specific one, but any level where we slice that particular surface, the tangent vector to that level curve is going to be orthogonal to the gradient of the surface. Because remember, what we're saying is here that the dot product is equal to 0. So this implies that the gradient of the surface is orthogonal to our tangent vector, r prime. So now if I were to go back and try to add that level of information or that additional information to my graph, I could say at every point here where I drew a tangent vector, I could draw a vector that is orthogonal to it, and then I could call that the gradient vector. So I could, for instance, I could draw a vector going here, and then it will be 90 degrees, and then here, 90 degrees. Again, they're not necessarily unit vectors, right? And then over here, maybe 90 degrees. So all of these now, these green vectors would represent the gradient vector at all these different points, right? So in summary, what this shows, what we've just proven, is that if you give me a surface and you want to find a vector that is orthogonal to that surface. Because notice, so what we're saying is that at all these different points, all these green vectors will form a 90-degree angle at that point with the surface. So the gradient is always going to be orthogonal to your surface, right? And again, I could draw lots more over here. So I could draw lots of other things here now, even without the curves. Now that I know the property, I don't need the level curves to be able to draw something like this. Once I'm on my surface, I could just draw something that is 90 degrees with it. Over here, it would be like this. And there you go. If I wanted, now assuming the top is flat, then I could do something like that, right? And so forth. And obviously, if it's wavy, like maybe over here, it's not quite pointing that way, but maybe it's pointing that way, and so forth, right? So the whole idea now is I know that wherever I can put the gradient vector, which again I'm using these green vectors, those vectors will always form a 90-degree angle with your surface. So even though the surface is curved, right? It's like the direction of the gradient just adjusts for the curvature of the surface in such a way that the green will always be orthogonal to my surface, right? So essentially, we have proven this theorem. So here is our theorem, right? And again, this is a second property of the gradient, and it says this: assume that my surface. Assume that this function has continuous first partial derivatives. That means our gradient vector makes sense, right? So has continuous first partial derivatives. Okay, I can't spell derivative. That's disappointing and embarrassing all at once. So, come on. So first partial derivatives, and let's just say the p0, so x0, y0, z0 is a point on the surface, so is a point on the surface. Now for the surface I need an actual equation, so that's where I'll just take the big F function and just set it equal to whatever constant it is. So like this. So on that surface, if our gradient of F, right, evaluated at, and I'll just write it like this, evaluated at P0. So I would plug in the x0, y0, z0 appropriately. So if that gradient is not the zero vector. So in other words, all my green vectors that I just drew, if they all have some well-defined direction, so then that gradient vector evaluated at that particular point is orthogonal, or we could say normal, or we could say perpendicular to the surface at P0, right? So as long as we have a surface where we can differentiate, so we have a surface in terms of x, y, and z. All the partial derivatives work nicely. Everything is nice and continuous. We have a point on the surface. Everything is nice and continuous at that point. Then if we were to compute the gradient of this function f, evaluated at the point, it will give us a vector that is orthogonal slash normal slash perpendicular to that surface, right? And again, it's another important property of this gradient. Now let's just do a quick example and kind of wrap this one up. Relatively short video, relatively, right? So find a vector that is orthogonal to the surface and let me just, instead of writing down the big F notation, let me just write down the equation of the surface. And I won't make this one super complicated, but you got x squared plus 4y squared plus z squared is equal to 18. And let's say at the point 1, 2, 1, just a simple point, right? So again, what we want to find now is a vector that's orthogonal to the surface, whatever this looks like. Don't think that this is not a sphere. It's not a sphere because we have this coefficient that's different from the other two. Essentially, this if you want to know what this is called an ellipsoid. It's basically a football shape, right? You know, so this type of shape, it's like a generalized sphere. It's been like squished in one of the directions. This is called an ellipsoid. Fancy word for your American football. Right, so you can have that picture in mind, and we want to find a vector that's orthogonal to that football shape at this particular point. Now, let's say you wanted to determine if this point is actually on the surface. It's pretty easy to check. Let's just double check that this works. So checking that 1, 2, 1 is on the surface, because sometimes you don't know, right? You don't want to try to plug in a point that doesn't even satisfy the equation. So checking that it is on the surface, what I would have to do is do the operations that are on the left and see if I get an 18. So let's see if this works. I'd have 1 squared plus 4 times 2 squared plus 1 squared. So this is 1 plus 16 plus 1, and it is in fact equal to 18. So there we go, right? So again, the problem makes sense, because you don't want to talk about, oh, here's a vector that's orthogonal to a surface at a point that's not even on the surface. That doesn't make any sense. What that would mean is my blue vectors are just kind of hanging there in space, right? Not what we want, right? So basically, I am going to define my big F. So the big F, we can just take it as everything that's on the left-hand side, and the constant in this case is 18. So we're going to define our big F of x, y, z as x squared plus 4 squared plus z squared. And then we need the gradient of this, right? So we're going to take the gradient of this, which again will be a function of x, y, z. And that's where we get our vector. So the gradient vector of this surface is 2x. That's it, because these other two terms, they don't have an x in there, so they're all constants. When you differentiate them, you get 0. The middle component is the partial with respect to y, and again, only the middle term here has a y, so the other two terms differentiate to 0. The middle term, we're left with 8y, and then similarly, first two terms here, when I differentiate with respect to z, I'll get 0. When I differentiate z squared with respect to z, I'll get 2z. So you can think of this vector now representing all for all the points that would be on this ellipsoid. this vector would give you a vector that's orthogonal to the surface. So this is always orthogonal to any point on the surface. And now at the specific point, so at 1, 2, 1, here's this, we can call it our normal vector. So at 1, 2, 1, we end up with the vector, so double the x, so 2 times 1 is 2. Multiply the y by 8 is what, octupling, something like that. So yeah, times 8, so that's 16. And then again, double the z, so we got 2, right? So whatever my football shape is, you know, we could sketch a football, put this point somewhere on that football, and then at that point, draw this vector. This vector must be orthogonal to the surface. And there you go. So another really useful, nice kind of geometric application of the gradient vector. See you in the next video.